conversions. For example, phenol hydrogenation and benzaldehyde hydrogenation using electrocatalysis to do the hydrogenation. So one of the things that they had been doing, and Nirala worked on early on, and part of this was the hydrogenation using electrocatalysis of things like phenol on platinum, rhodium, and those types of metals, and then comparing that to simple aqueous phase hydrogenation with dissolved hydrogen gas on the same catalytic materials with the same reactant molecules. And the voltage that changes the potential of the protons or the chemical potential of protons in the solution increases the reaction rate in the same way that increasing the hydrogen pressure when you're doing aqueous phase, just normal thermal hydrogenation increases the reaction rate. And in fact, if you get situations where we think that the coverages are sort of similar, which is a little bit hard to convince yourself that you're right about that. But if you make your best attempt and you look at the activation energy for apparent activation energy for the electrochemical hydrogenation and the thermochemical hydrogenation, in this case, of phenol, it's almost the same, which suggested similar mechanism, and other evidences suggest that as well. And what it seemed like to me is that the mechanism was the addition of adsorbed hydrogen to the adsorbed organic in the rate determining step. And some of the collaborators at Phenol and other people around the world had a strong opinion that that the hydrogenation was happening by direct attack of the adsorbed organic by protons from the aqueous solution, which I had intuition reasons not to believe, and I hope to convince you that we have better evidence for this mechanism that I propose, and that led to the questions that we asked further on that become really the focus of this talk. So this is a kind of a classical kind of a plot that you might make if you were doing experiments in the gas phase kinetics of catalysis that I'm so used to. It's just measuring the rate as a function of a reactant concentration. And this had been done, of course, for, this is the turnover frequency versus phenol concentration during thermal aqueous phase catalysis.
I just called them and they are sending me the codes.
Somebody needs to mute them.
Can you please mute yourself?
Call them.
Thank you. So, and this region had only been measured previously, but no. Was that you asking me to unmute, Karen? Did I do the right thing?
I think you're fine.
Okay.
We can hear you. Thanks.
So the anyway, that I figured if we increase the phenol concentration, we might see a rollover. In fact, we did see a rollover in the reaction rate as we increase the concentration, quite a dramatic rollover. We could fit this with kind of a classic Langmuir-Hinshelwood kind of kinetics, where the rate was proportional to the coverage of adsorbed hydrogen and the adsorbed phenol, in this case, organic. We fitted the data, and this is room temperature data, to get the equilibrium constant for hydrogen absorption with a funny reference state here, but so it's a funny number, unitless. But equilibrium constant for the adsorption of the organic phenol. And the thought occurred to us that, well, if we can do this, we better make sure that this phenol equilibrium adsorption constant that you use to fit the kinetic data is consistent with what you might measure independently. So we set about to measure the equilibrium constant for phenol adsorption in aqueous phase independently from the fit value that comes out of the kinetics. And so then once we measured that equilibrium constant, we realized that we could estimate adsorption energies in aqueous phase from that, and that leads to the interesting things that I'll talk about. We measured this was Neurella's idea, measured the amount of adsorbed phenol by looking at how much it blocks the hydrogen adsorption in cyclic voltammetry. And so this is the cyclic voltammogram of platinum 111. This is the hydrogen adsorption desorption region, and the peaks can be assigned based on single crystal experiments. Not shown here is a big broad part here that kind of looks like this. You can see my cursor that shows that's the part due to the terrace-like, platinum 111 terrace-like sites. And so as you add phenol, the sites get blocked first that have to do with the more coordinatedly unsaturated sites, and it takes higher concentrations to block the 111 type sites. And people had Sasaki had pointed out that you could estimate the phenol coverage by sort of 1 minus the amount of hydrogen that's adsorbable, and you can quantify the adsorbable hydrogen from the areas under these peaks. And so we took the data from Sasaki and plotted it up, and sure enough, you get something that looks like a kind of a Langmuir adsorption isotherm. If you're just looking at, this isn't true one, this is just a relative number here, and only looking at the attenuation of the first part of this. And you can get an equilibrium constant out of that. And as we went along, we realized that this equilibrium, it takes much, much higher concentrations to block the hydrogen adsorption sites on the terraces. And so we pushed this curve to higher concentrations and saw that we could also block the terrace sites. And you can figure out which sites are being blocked from the line shape of that. And so there's two kind of equilibrium constants here. One is for what we call the step sites or low coordination sites. And that's, we've turned the equilibrium constant here into a delta G, standard delta G0 for adsorption. And then these sites, as they're being blocked, are the terrace sites. And so we get from the amount of hydrogen that's adsorption that's being blocked, the coverage, really, this is the relative coverage of the phenol on the site. So it goes up with phenol concentration on the step sites. It takes much higher, orders of magnitude higher to populate the terrace sites, and a different equilibrium constant in delta G0 for that process. And so we did that for several hydrocarbons, and it was nice because we were able to see that this kinetic fit that gave us an equilibrium constant was very close to the equilibrium constant that we measured independently, albeit only for the terrace sites. And that is a not inconsistent with, or is consistent with, quite consistent with the effective particle size. So as you go to smaller particles, the activity goes down per unit area of platinum. And so based on those kinds of measurements that had already been postulated from the Pina and L group, that it was the more coordinatively saturated terrace-like sites that were responsible for the activity of phenol hydrogenation. So that seems like terrace sites are the place where the action is happening on these powdered. I didn't mention, but the catalysts we're studying the activity for here are the form of powdered platinum on carbon support. But what troubled me at this point in time is this phenol was adsorbing and desorbing in equilibrium easily at 298 Kelvin. And I thought that was impossible for the kind of phenol I was used to. We had just measured phenol adsorption on platinum 111 and nickel 111 and by calorimetry. And the heat of absorption is giant. It's like 200 kilojoules per mole. And then when you populate the first layer, it drops off. This is at low temperature, so we also populate the second layer and the third layer and multi-layers. This is the interesting part that's binding to platinum. It's a high heat of adsorption, and then it decreases with coverage, and then it drops down to the multi-layer heat. So if you know about your equilibrium adsorption desorption, if you have a heat of adsorption that's on this order of 150 to 200 kilojoules per mole, you're never going to desorb it in any reasonable time scale at room temperature. So how the heck are we able to get phenol to adsorb and desorb equilibrium at room temperature so easily during thermal catalysis or electrocatalysis? And so I set about to try to understand, or we set about to try to understand that. I should point out that the calorimetry data for benzene on platinum and nickel is almost the same as these calorimetric data for phenol. And so the dominant binding of these two molecules is through the benzene ring interaction. It sits flat on the platinum or nickel surface and has a very strong adsorption, at least in the gas phase. And so let's compare the thermodynamics of the gas phase with the aqueous phase. And this is the gas phase adsorption, phenol in the gas going to adsorb phenol and platinum. This is aqueous phase, phenol in the aqueous phase, dissolved in the aqueous phase, going to phenol adsorbed on platinum with water on top of it. And we can sort of connect this thermodynamic cycle because we know the Henry's law constant for water, for phenol dissolving in water to make aqueous phenol. That's been measured, Henry's law constant, and its temperature dependence has been measured. And from its temperature dependence, Rala fitted it with sort of standard equilibrium thermodynamic thinking to get that the heat of solvation is 50 kilojoules per mole for phenol. It's downhill in energy, enthalpy 50 kilojoules per mole to dissolve phenol. And so we know that difference. Let me explain how we get this number. We had, or these two numbers, we have an equilibrium constant that we measured for this, and a delta G0 that we measured for this. And we could get the delta S from the Henry's law data for this step. And we also said if the phenol has the same sort of structure on the platinum surface, its entropy ought to be about the same, whether it's got water on top of it or whether it's in the gas phase, if it has the same kind of binding, that flat geometry to the surface. And we know how to calculate the entropy that for the adsorbed phenol in the gas phase. We assume that was the same here. And so we could turn the delta G's into delta H's by correcting for the entropic contribution to the delta G. And that is how we got this number here. And so these are now all enthalpies It's around 200 kilojoules per mole downhill to absorb phenol in the gas phase. Depending on the coverage, this drops down to 150. It's about 21 kilojoules per mole downhill in the aqueous phase. It's 71 to go from gas phase phenol to aqueous phase phenol. And that difference is just associated with this heat of solvation of phenol and water. And how can this be? Why is there such a huge difference between the heat of absorption of phenol in the gas phase and the heat of absorption of phenol in the aqueous phase? Is it possible that that is the same kind of structure and nature of binding of the phenol to the surface when there's water around? And I thought, not to be the same structure, but it sure enough, I think is similarly the same structure. Let me try to explain how we do this. So I'm saying this phenol absorbs on the platinum and UHV or in the gas phase, and on the water, there's a huge difference in the heat of absorption, but I hope to convince you that it still has a geometry similar to this, and the nature of binding can still be the same, the opposite of what I set out to prove when I started trying to go through this. So this is a bond additivity model that we developed to try to understand the nature of all of the effects of the solvent on this process. And let me step you through this because this may be the most important slide in the talk, and it is one that came about because we were dealing with this flat molecule. But as I'll show later, I think you can go through the same kind of thought process with things that are not so flat, and work out some simple corrections to it. Let me take a step forward first here and just think about something, the first part maybe of this. Imagine that we're going to take phenol or benzene and put it in water. So this is just the heated solvation for this step. And I'm sort of picturing this, if you look down from the top, this would have the cross-sectional area of the phenol molecule or the benzene molecule. Here's your column of water that is infinitely long, if you like. And we're going to stick this phenol into the water, and that's solvation from the gas phase. And what's involved in that, in sort of a bond additivity kind of a picture. And we're going to neglect, in doing this, the edge of the phenol molecule or the benzene molecule because it's thin compared to the area here. And so the first step is to break the water-water binding to make a place for the phenol. And that energy we know, it's just the surface energy of liquid water for this surface and this surface. And those surfaces have the surface area of one phenol, adsorbed phenol. And have to multiply it by 2 because you get 2 surfaces. So by definition, that's just the surface energy of water times 2 times the area. And then we stick the phenol into there. And when we do that, we make a bond between the phenol and water here. And we make a bond between the phenol and the water here. And I'm going to call that bond energy the water phenol bond energy. And this is downhill by 2 of those bond energies. So that's the kind of thinking that goes into this. Since we know this heat of solvation is about 47 and a half kilojoules per mole, we can extract out of this the strength of one of these water phenol bonds, that is the binding energy per mole of phenol of water, liquid water, to one face of the phenol, and that's about 50 kilojoules per mole. So let's back up and look at the full process. Okay, what I just described is this solvation of phenol. Now I have R for phenol. Solvation of the phenol in the solvent. That's all this is. The net reaction is to take gas phase phenol and put it underneath the solvent and on the surface of the metal. And so this part from here to here is just what we measured with our cyclic voltammetry to get the equilibrium constant of going from aqueous phase phenol to phenol on the surface in aqueous phase of platinum. And so what's involved in that part? I just described this part. Now I'm using S for the solvent instead of water. So what's involved? Well, the first thing you have to do is you have to break the binding between the water and the platinum. And so that's the delta U for the solvent metal binding in the area of one adsorbate. And that by definition is just the adhesion energy of the solvent to the metal times the area of the molecule that's going to adsorb. So you have to detach the solvent. And then the second step is we're going to break the solvent binding to the organic on one face of the organic. And we already determined that over here and in that last slide. That's just one of these solvent organic phase bond energies. And then we're going to take this solvent stack and we're going to bring it up and stick it on top here. So this guy moves up there. And that's just making the solvent-solvent binding, which again, by definition, is just the surface energy of the liquid solvent times the area that you're doing that for, which is two faces we have that bind here, this face and this face. So we have a factor of 2. So that's downhill in energy. By that, we know that number. We know the surface energy of liquid water. And then finally, we take this face of the water that has phenol on it, the bottom of it, and we bind it down to the metal. And within this approximation, we would say, well, we're going to say that the binding energy between the phenol molecule and the platinum is about the same as it is when you adsorb phenol from the gas phase. So we can go through those numbers, and the absorption energy from the gas phase is about 200 or 150 kilojoules per mole, depending on the coverage. The absorption energy in the solvent, the net process, from here to here, is 21 kilojoules per mole. The adhesion energy of the solvent metal interface in the area of the phenol is about 116 kilojoules per mole of phenol. The solvent binding to the phenol is about 50 kilojoules per mole. I showed you that in the last slide. And the surface energy of the water on the surface of the surface area of the phenol is about 50 kilojoules per mole. So we sort of know all of these numbers, and we can compare this side with that side to see if they sum up to be about right. And there still remains a difference of about 160 kilojoules per mole if you take, for this energy, the high limit here. It drops down to only about 10 if we take the lower limit there. So we were pleased with that. Part of the reason that the experiment in water for getting the heat of adsorption was measured in the limit of low coverage, it doesn't change with coverage like it does in the gas phase, but I think there's an explanation for that, which is the hydrophobic effect. If you put water and phenol together in 3 dimensions, they separate. They don't want to be together. And I think the same thing happens in a two-dimensional layer on the surface. If you mixed water and phenol on the surface of platinum, the phenols would separate to one area and the waters would separate to another area, because you don't want to break up the water-water strong hydrogen bonding there. And so I think in the aqueous experiment, we always have the high coverage limit. And so I don't know, there's only so far you can go on that. The driving force to separate those phases in 3 dimensions is about 20 kilojoules per mole. So maybe you can only get 20 kilojoules per mole out of that, not the full 60. But it's getting now a lot better. Because remember, to start with, we were trying to explain the difference between 200 and 20 for the heat of adsorption. And so we've gotten most of it out of this picture that I drew there by simply considering the adhesion energy of the solvent to the surface and the other sort of water or solvent organic bond effects. The dominant one is the adhesion energy at the surface. This has major implications with respect to catalysis. In starting to understand this, one of the things that I had a hard time understanding is how one can do aqueous phase reactions on platinum and rhodium and palladium at room temperature with these organic aromatic molecules, because I knew that they just should be just plugging up the surface if they had anything like the heat of adsorption that we measure in the gas phase. But the fact is all of these effects mean that it's only sort of 20 kilojoules per mole uphill to desorb a phenol from platinum into the aqueous phase, even if the nature of the binding between the phenol and the platinum is the same sort of 200 to 150 kilojoules per mole that you have in the gas phase.
So Charlie, just wondering if this is about a good time for us to do our first Q&A?
Yeah, let me,
Okay.
yeah, it's the perfect time. Let me just do the one last slide that I was looking at there. And the point I just wanted to make here is when we look at this Langmuir kinetics, Langmuir-Hinshelwood kinetics, you get to high phenol concentration, and sure enough, eventually you do saturate the surface so much that you poison the catalyst at room temperature. But it takes a hell of a lot higher concentration of phenol or effective hydrogen concentration in the gas phase to do that than would happen at room temperature or in the gas. I mean, in the gas phase. In the gas phase, you have to go up to like 200 degrees centigrade to do any catalysis with these organics. Otherwise, they're poisoning the surface. Whereas they happily do catalysis at room temperature in the aqueous phase, and this explains that. So yes, it's a good time to take questions.
So we'll have Nitish, who is a postdoc at Cat Theory, moderate the questions. So I see that we have one already.
Yeah. Okay. No, I think there's. Yeah. Okay. Can everyone hear? Or...
Yes.
Okay. Great. So there's one question by Tet Choksi from NTU Chemical Engineering, and the question is: can you discern if phenol binds in a vertical or a parallel configuration on hydrogen-covered surfaces from experiments?
There's probably a way to do that, and we haven't done that, and our group is not skilled in those kinds of things. It's pretty challenging to do that in aqueous phase. I have to say it's a good question, because that's what I thought at first was going to be the explanation for why the heat of absorption was so low in aqueous phase compared to gas phase, was that surely the phenol must be taking on a totally different geometry. But I think what this bond additivity model proves is that it's not the case. I think that the phenol in aqueous phase, according to the thermodynamics that I just went through, could very well be just almost the same kind of nature of binding as in the gas phase or an ultra high vacuum.
But I would guess that as you increase the coverage, just because there's lesser space available, that would switch to this vertical like configuration, right?
That happens on something like silver. It's well known that when you put an aromatic molecule on the surface, or a phenol or a something with nitrogen over there instead, or something, that they do stand up as you go up in coverage.
Yeah.
But that doesn't happen with platinum and palladium and rhodium, to my knowledge, even in the gas phase. Or in the gas phase. It's just because the binding is so damn strong of the aromatic ring, to the metal surface, when it's platinum or palladium or rhodium compared to silver,
Yeah.
Yeah.
Great. Okay. So the next question is by Ben Wang from Oklahoma. And the question is, in the rate equation, hydrogen and phenol compete for sites, which is also shown in the CV measurement. I'm wondering if someone has done phenol hydrogenation in gas phase and shows these two compete for sites.
Yes, and I don't know about phenol. My memory's escaping me a little bit, but benzene, and by the way, the kinetics and so forth are quite similar for benzene, and the absorption energy is quite similar. And in fact, for is it benzaldehyde, I guess, convinced ourselves that our approximations about the entropy were the same. Calorimetry had been done in the aqueous phase, and the heat we got out of the CV measurements and the approximation about the entropy came very close to the heat from the direct calorimetric measurements in aqueous phase. But, that's an aside. But it's complicated, more complicated, in the gas phase, because you have to crank the temperature up. And by the time you get up hot enough in temperature to be desorbing these 200 kilojoule per mole or 150 kilojoule per mole molecules in the gas phase, you start breaking carbon-hydrogen bonds, and you build up heavily dehydrogenated. Somebody really needs to mute their microphone. All kinds of banging around somewhere.
Sorry, someone is not muted, and there's some disturbance. So please.
Yeah.
Yeah. Okay.
This person.
Okay.
You start poisoning the surface with too heavily dehydrogenated fragments of phenol or benzene in the gas phase, and it gets very complicated. And Val Van Ice has worked out a lot of those kinetics, but certainly the same kinds of elementary steps and site blocking do happen, but there's more serious site blocking due to other things besides the aromatic, due to the more heavily dehydrogenated aromatic. If you get a real high hydrogen coverage, you can prevent that. And it looks more like what I'm showing here in the aqueous phase.
Okay, great. The next question is from Hongfei Lin. So would one phenol molecule pairing with two water molecules be oversimplified? I'm not sure what that means.
Yeah, I don't know. I think that the mechanism is that hydrogen gets on the surface, is absorbed hydrogen atoms from in the aqueous phase thermal catalysis that happens from a H2 molecule somehow interacting with the platinum, the dissolved H2 molecule. In the electrocatalysis, it happens from a proton getting reduced to make an absorbed hydrogen on the surface. And then that thing just adds to the phenol or the benzene or the benzaldehyde. So.
Okay. So the next question is from Megha at DTU. And the question is if other protic solvents would have a similar effect.
Yeah, let me get to what the effects of different solvents are, because that's the next part of the talk. So that maybe that's a good segue to start the next part of the talk. Does that sound reasonable?
That sounds reasonable. Yeah, I think the next question is also related to different solvents. So I think we can move on to the next part, and then in the end we can.
Yeah, so
So those,
there's so many. We'll continue after. Yeah.
okay.
Yeah. Okay.
But those two questions are perfect, you know, because they
Lead up to your next part. Yeah.
What's that?
I said they lead up to your to the next part of
Yeah,
your
exactly.
Yeah.
Perfect. Yeah. And so first, let me explain to you how we measured the adhesion energy that was used in this bond additivity models. I pretended like it was known, but to tell you the truth, adhesion energies of solvent molecules to clean metal surfaces are simply not known. You can't look those things up. Even water, the adhesion energy of water to platinum, clean platinum, you can't look it up. And so how did we get it? And I realized that we had been measuring adhesion energies at solid-solid interfaces for some decades in studying metal adsorption and metal nanoparticle binding to support surfaces. And we derived this adhesion energy thermodynamic cycle that allows us to calorimetrically measure the heat of adsorption as a function of coverage as we build up a multi film of metal of the heat of adsorption integrated up to multilayer coverage is all we need to get the adhesion energy at this solid-solid interface. And so we can apply that to solvents, and this is the same diagram for solvents. We have solvent molecules in the gas phase and the clean metal surface. We calorimetrically measure the integral heat of adsorption as we build up a multilayer film of the solvent on the surface. And we do the Gedunken cycle, where we take a slab of the solvent and attach it. That by definition is the adhesion energy of the solvent to the metal. And these things we know, this is the heat of vaporization of the solvent molecule. And this is the heat of, or the surface energy of the liquid solvent, which we know from many solvents. And so we can extract out of this, from these measurements and these literature values, the adhesion energy. The trouble here is that we when we can do this experiment and make multi-layers of a solvent, it's at a condition where it's a solid instead of a liquid here. But we go through some arguments in this paper that show that it's not too far off, and it takes a while to prove that. So I'm not going to go through that part of the arguments here. Please look it up here, because it's a quite logical argument how doing this with the solid slab is about the same, because we use the liquid values for these things and other reasons. The type data then that we use to get that is shown, for example, here for methanol on platinum 111 at 100 Kelvin, heat of adsorption versus coverage. And it stays high in the first layer. It's a little bit higher than the multi-layer in the second layer. And it drops down to the bulk layer by the third, bulk heat of sublimation by the third layer. And it's really this integral area that's blue here, the shaded area, that's this number. And that equation I just showed you has all of that shaded area in it for the adhesion energy, plus 2 times the surface energy of the liquid solvent, which we know. And so we can get the adhesion energy out of methanol to platinum out of this calorimetric measurement of the integral heat of adsorption there, or how much it is above the heat of sublimation, if you like. So basically, the assumption here is that the heat capacity going from 100 Kelvin up to the room temperature is the same for the solid as it is for the adsorbed layer of the methanol. You can kind of test the limits of that. Similar measurement for formic acid on nickel. Again, the shaded area gives us the adhesion energy. If we know the surface energy of liquid formic acid in this case. So those are three different solvents. The data we used to get the water was for DQO on platinum 111 from this old paper. So here is a summary of the adhesion energies that we measured in that way for different solvent molecules, 5 different solvent molecules, and on 2 different single crystals, clean single crystals. And to my knowledge, these are the first estimates, experimental estimates of adhesion energies of solvents to any clean surfaces ever published. And methanol has the weakest adhesion energy per unit area, and it gets stronger as you go to aromatics. Here's our water, it's kind of intermediate. And let me sort of address one of those questions that you can already see here. Or let me go one more step and just to, so look at this number, 1.5 about for methanol on platinum 111. We also extracted out of other heat of adsorption versus coverage data determined for linear alkanes by temperature programmed adsorption by Steve Tate when he was in my group in collaboration with Bruce Kay and Zdenek Donalek. And we extracted the adhesion energies of those linear alkanes as a function of chain length on graphite and on MgO, and we could only get cyclohexane or hexane, N-hexane on platinum. Look at this number, it's about 1.5 for for hexane on platinum. It's very similar per unit area to methanol there. So alkanes are over here, methanol works up. So suppose you had a solvent that was an alkane or methanol instead of water. Well, so water is like 3, and these guys are like 1.5. So they're half as much, their adhesion energy is half as much to the surface per unit area as water. And that means that there's going to be sort of 60 kilojoules per mole higher heat of adsorption of phenol or benzene if you're doing it in those solvents that have these low adhesion energies, according to that bond additivity model that I developed. So there's a huge tunability in what you might do with the choice of solvent that you can see already here. You'll have to go to higher temperature if you run the reaction in an alkane, because the alkane has a lower adhesion energy. So you're going to have sort of 50, maybe 60 kilojoules per mole higher activation energy to desorb the molecule. It'll probably saturate the surface if you try to run the catalysis at room temperature in those solvents. But it might behoove you to go to somewhat higher temperature so that you could run the reaction and break some bonds you want to break or something. And so maybe you don't want to do the catalysis at room temperature for the reaction that you're doing. So I hope that's starting to answer some questions about that. I think these adhesion energies are giving a lot of ideas to me about how you can use them as a knob for tuning things like the branching ratio and surface reactions between desorption or catalysis between surface reactions versus desorption, right? That if you change the solvent you have an adsorbate on the surface, it's gonna not, its step where it does something on the surface like break a bond or add a hydrogen to it, maybe that step's not so affected by the solvent because it's all this binding of the molecules to the metal. It's all kind of similar because the solvent's sort of a weak effect here. But to then take this guy out off the surface and desorb it, that's a huge difference with different solvents, because the solvent then comes in and replaces those bonds in that area. And so I think you can really control branching ratios in catalysis by thinking about those and the proper choice of solvent. I'm just calling here for things like DFT calculations to look into some of these things, and because I think there's lots of opportunities with computational catalysis to do these kinds of ideas, and also to explain trends in adhesion energies with different solvents, and that really just relates to the bond strength per unit area there. Yeah, I just wanted to put this in here to remind myself to talk about, we neglected edge effects in these pictures where we were breaking water apart and sliding in a molecule in between the two water layers or the two solvent layers. And if you think through it, and your molecule has some shape to it and thickness to it that you're absorbing, there's you can sort of picture of a dividing line here, and this is the top face and that's the bottom face, and so the solvent interacts with this, which is over a projected area, and the solvent interacts with this. When you break it apart to keep solvent on the top and to remove the solvent on the bottom, so that then you can put the bottom down to your metal surface, for example, as long as the thickness of the molecules is not so huge that there's a lot of solvents that bind in this area after you get it on the surface, I think this dividing line concept is not a bad one. You know, think through from simple van der Waals interaction type things, and I think you will start to see what I mean. It's a little bit of a complex thought, but I should thank Jack Romps, who's a graduate student in the group now, who did these taking already published calorimetric data for these solvent molecules and extracting out of those these adhesion energies using this thermodynamic cycle. And in fact, his paper has a much prettier sort of explanation of this equation that we use for that, and also of the bond additivity model might be better explained in that, or just the symbology, I guess, is a little bit easier to read in his paper. Okay, I'm going to switch gears completely, but I want to talk a little bit about something where adhesion energy again, is a really important concept and plays a major role. And that has to do with nanoparticle size and support effects in catalysis. And so in both aqueous and phase and electrocatalysis and gas phase catalysis, the late transition metals are usually in the form of nanoparticles on some support material. The support tends to be carbon in electrocatalysis, but it can often be oxides in the other kinds of catalysis. And we know from experience that there are huge effects of particle size and of the support material on catalytic performance. And the centering is also a big problem in catalysis, and that is something that is of a great interest to industrial catalysis people because of the loss of activity with time. It's a slow process maybe, but if you put a commercial catalyst for large reaction, things like making ammonia or making methanol, or doing things to convert hydrocarbons to different fuels or so forth. You need the catalyst to last a really long time. And so deactivation is a big problem. And both of these things can be understood, I think, best as a first sort of a pass from understanding how the metal atom's chemical potential in these nanoparticles varies with the particle size and the support material. And that really is related strongly to the adhesion energy at the interface between the nanoparticle and the support, as I'll show here. And that chemical potential is just, it's got some entropic concerns in it, but for solid binding and so forth, metal atom's chemical potential is, to a first approximation, just the energy stability in terms of internal energy of the metal atoms in the material. And so let's think about predicting how the chemical potential, this energy stability, depends on the size and the support material. Without a support, already people for many years have understood how chemical potential varies with particle size for spherical particles. These kinds of things were derived to understand particle size effects in the thermodynamics of things like the nucleation and growth of water droplets in the clouds and the eventual formation of rain. And the Gibbs-Thompson, ancient Gibbs-Thompson equation here says that the chemical potential of something in a liquid particle of radius r above the bulk chemical potential in the bulk of the liquid is so reference to a chemical potential of 0 for infinite radius, if you like, is 2 times the surface energy per unit area of the material, the molar volume of the material divided by the radius of the particle. And we just take that over from things like water and instead think about a liquid droplet of a metal. And so this is now the chemical potential of the metal atoms. This is the surface energy of the metal in that. And then we can do it for solid metals. And this is just the surface energy of the solid metal. And this is the chemical potential in the solid metal. The same derivation works fine. But this doesn't consider adhesion energy at the interface between the particle and the support yet. And so only recently, I couldn't believe it, but only recently did anybody, and that was us, think to include adhesion energy in this derivation that Gibbs and Thompson did. And so we considered here a hemispherical particle attached to a support. And the adhesion energy is the binding per unit area between the metal and the support. And when you go through the same derivation of chemical potential, you get that it's 3 times the surface energy of the metal minus the adhesion energy at this interface times that same molar volume divided by the radius. And so it shows you that if you have stronger adhesion between the metal and the support, you're going to have lower chemical potential. So the metal atoms are going to be more stable in the particles if they're on a support to which there's a strong adhesion energy. That sort of makes qualitative sense, and it's quantified here for the first time. And so we knew adhesion energies for a lot of systems from those same kind of measurements that I talked about starting back in 1997. At that time, Larson, who's now sitting in the audience there and is your chairman of your director or whatever of your department, Jena Hovbeck Nielsen, I hope I'm saying that right, was the first author in this paper where we tabulated adhesion energies of silver to different support surfaces. And so we could use those kinds of things that had been determined for a long time in my group to get at the predictions of this equation that we derived that had this term in it and this term in it. And those predictions are shown in these dashed curves for all of these different systems: copper on Syria, silver on Syria, gold on Syria, silver on iron oxide, silver on MgO. And the predictions fail in the small particle size regime. The data are shown here. We measure these data with our calorimetric techniques from differential heats of absorption. And we realized that all of these differences could be patched up by a simple empirical correction where D0 is 1.5 nanometers, and this is diameter instead of radius now. And the reason that that correction is needed, notice what this does. If you have a diameter of 1.5 and this is 1.5, you've doubled at that diameter the effective value of this pair of constants. And we already had known and had even published science papers about the fact that this term increases dramatically with decreasing particle size in this size range. And the reason is that when you have a giant particle of a transition metal, for example, you have mostly if it's a face-centered cubic metal, it's mostly 1-1-1 planes on the surface of a giant particle. Whereas when you get smaller and smaller, you get more step edges and more kink sites. And we know that those are more costly energetically. So the energy to create those surfaces that are of high radius of curvature increase as you go to decreasing particle size. And there's also literature that says adhesion energies also increase as you go to decreasing particle size. So we just put this in as an estimate of the that behavior and use this as a parameter, and found if we put 1.5 in, it fits all of these data pretty darn well. So now we have, for late transition metals, a predictive equation, I would say, for how the chemical potential depends on particle size. And the only thing you need to know, that these are known for all the transition metals, the surface energies. The only thing you need to know is the adhesion energy at the interface. And I'm not going to go through all the, in some cases, quantitative equations that explain the importance of knowing this chemical potential versus particle size in catalytic performance, but we have summarized those in this paper published here, where we came up with this empirical correction factor to the equation that had been derived in this earlier paper. What did I do? There, so I should thank my recently graduated student, Zhong Tim Mao, who was the author of that work. And if we can just get these adhesion energies, then we'll have, and start to predict adhesion energies at metal support interfaces, we will have a huge predictive ability for particle size effects right down to the smallest particles on catalysis. These things correlate with catalyst activity, or the strength with which the catalyst binds molecules, and correlates with the sintering rates in a very quantitative equation-like way. So can we learn about the systematics of adhesion energies? Well, we're making some progress on that, but not as much as I wish. If we have a single support, in this case MgO, and we measure the adhesion energy and do it for different metals across the periodic table, we found that it correlates very strongly with the this axis, which is, this thing is like the oxophilicity of the metal. And so copper is more oxophilicic than silver and gold. And this is, what is this number? This number is the difference. It's this is the how much, if you like, downhill in energy it is to go from gas phase metal atom plus the oxygen gas to make the most stable oxide of that metal. And so this is, in my opinion, a measurement of the oxophilicity of the metal atom. So that's why I put this here. This is the surface area of the metal atoms. So this is the atomic volume in the bulk to the 2/3 power. So it's the surface area of the metal atom, if you like. So this is kind of an oxophilicity per unit area. These are per unit area numbers, and that's why you need this addition to the oxophilicity there. So there's a strong correlation. Recently, we realized that nickel would be way over here, and we measured nickel, and sure enough, the data point for nickel is way over there. So this is a predictive equation, fitting, if you like. This equation is predictive almost, approximately, for adhesion energies on a given support, if you know the others. But as you change from one support to another support, there's a huge offset. The slope seems to stay about the same, but there's a huge offset depending on what support you go to. So most of the points that are on, that we can make a line here are from, are the only points where we have multiple points and make a line. And now we have nickel in it also, is right where it should be for slightly reduced Syria. So adhesion energies are much, much stronger to Syria than to MgO. But the correlation, oxophilicity per unit area, is still there. By the way, why is the adhesion energy depending on the oxophilicity of the metal? That's because the dominant, and DFT calculations are what informed us about this. The dominant binding between metals, even as individual atoms and oxide surfaces, is to the oxygen atoms of the oxide surface, not to the metal cations, but to the oxygen. So it's mostly metal, these metals, and they're binding to the oxygens of these support oxides that determine the strength of this binding there. So, okay, how am I doing for time, Karen?
So, I mean, originally we had you scheduled until 9:15 your time, but of course we can take questions past that. So now
Okay.
it's 9:09.
Okay. I had one last slide of stuff I wanted to show here. I showed you this. I showed you this equation today in some detail. Two others I'd like to just touch on is that we understand now that the apparent activation energy in catalysis is a weighted average of the enthalpies of all of the intermediates and transition states in the catalytic mechanism, each weighted by its degree of rate control. So if you've ever used degree of rate control, go look up our paper where we show this. And we've also shown that the kinetic isotope effect in catalysis can be calculated from a microkinetic model. You need a microkinetic model for this and for this. Can be calculated from the difference in the standard state Gibbs free energy between the two isotopes, multiplied again by this weighting factor that's the degree of rate control, summed again up over all of the intermediates and transition states in the catalytic reaction mechanism. And these two equations explain a hell of a lot about kinetics. If you're interested in the connection between, for example, DFT microkinetic model energy diagrams and experimental observables like apparent activation energies and kinetic isotope effects, so go look at those things. I thank the funding agencies, NSF and DOE, and I have the wrong, or I didn't save the last changes or something. I have the wrong acknowledgement slide here. Sorry about that. Yeah. Oh yeah, I have NSF in the University of Washington down here. Sorry about that. This was mostly funded by DOE. Okay, thanks, Karen. Sorry about that. A little bit extension.
Great, thank you so much, Charlie.
Mm.
Let's have now then the second Q&A, which I think Nitish, you can moderate. Yes.
Yeah.
So
Let me start with the. Okay, I think we can go back to the questions that were asked just before the second part of the talk, and I can just try and repeat. So I think the first question was the other protic solvents, which I think you discussed about a bit. And there's another question by Sihang, and the question is, I'd like to know if the coverage effect for phenol or other organic molecules also changes with other solvents, and how can you take both the solvation and the coverage effects into consideration? Not sure.
The answer is I think we don't really know yet, and you know, it makes sense on the one hand. What I said for an organic adsorbed on a surface and in water, for example, because of the hydrophobic effect, that in the first layer even, you would want the organic to be in one area or patches on the surface and the water to be everywhere else because the waters want to be together. But that sort of neglects the fact that there's these strong repulsive interactions between the organic molecules oftentimes on a surface because they have a dipole moment that points in the same way. I will say, though, that our experimental evidence is as follows. In the gas phase, whenever we measure the heat of adsorption of these kinds of molecules, or almost anything for that matter, unless they're things like water that want to make islands, you know, most adsorbates that aren't doing strong hydrogen binding and stuff, because of their interaction with the surface, they have a downward, usually, or sometimes upward pointing dipole moment. And when you have dipole moments that point in the same direction next to each other on the surface, they repel each other. And so there's usually repulsive interactions that cause the heat of adsorption to decrease with coverage when you measure it in the gas phase or in ultra high vacuum. And so you see a big dependence of the heat of adsorption on coverage. Mm-hmm. When we measure these equilibrium constants versus coverage, coverages versus concentration, and extract out of that equilibrium constants, we do have to allow that enthalpy to change some with coverage to fit the data, but not nearly as much as it changes with coverage in the gas phase. And my thinking on the reason for that is because of the hydrophobic effect, and I've only measured it in water. Hydrophobic effect causes it such that even at 10% of saturation or 5% of saturation coverage of the organic, it's already in high coverage islands that aren't going to get any higher in coverage. And I don't know if that high coverage is as high as what you get when you do the experiment in the gas phase. It might be quite a bit lower because you kind of get too close together and there's too much repulsion and you can't get any closer than that. But the coverage effects might be less, I'm guessing, in solvents because of those type effects than they are in the gas phase. Yeah.
Okay, great. Question by Tej Choksi again from NTU Chemical Engineering. It is very interesting that you have a constant DO of 1.5 nanometers for silver, gold, and copper nanoparticles. This coefficient likely arises from finite or quantum size effects. Thus, for small nanoparticles, would your model imply that at least from experiments for silver, gold, and copper, the finite or quantum size effects are similar in magnitude?
Yeah, I think it's not as complicated as a quantum effect. I do believe that this number here could be understood if you simply used like Leonard-Jones potentials and tried to calculate these things with a simple pairwise atom-atom model, binding model. And for the same reason that you could estimate the effect of step edges and kinks on the surface energy, let me remind you that if you look at the surface energy of a metal, like an FCC metal or an HCP metal, might be easier to think about from a Leonard-Jones potential point of view. The 111 surface, let's go FCC, it's easier for me to get the faces. For FCC, the 111 surface has a lower surface energy than the 100 surface. And that has a lower surface energy than the 110 surface. And when you go from the 111 to the 100 to the 110, you're going from metal atoms on the surface that are missing 3 nearest neighbors compared to the bulk, 4 nearest neighbors, and missing 5 nearest neighbors compared to the bulk. And that's why the surface energy goes up, and you would get that if you just had some dumb calculation of surface energy using some kind of a dumb Leonard-Jones potential for metal-metal interaction and a pairwise bond additivity there. And so, and you can kind of get the same thing from for adhesion energy effects. It's harder there to think about how to do that with pairwise bond additivity. So I don't think it's as complicated maybe as your question implies to understand why you have to increase the surface energy when you get down to these really small particle sizes. And I think it's the same number for different metals because they're all about the same size, you know? There's not that big of a percentage difference between the size of a silver atom and a copper atom and a platinum atom and a palladium atom, you know? So.
Great. Next question is from Jeff Lowe. I'm not that familiar with phenol hydrogenation, but has anyone looked at phenol hydrogenation in different solvents experimentally to validate your results that solvent adhesion energies can be used to tune reaction rates?
No, that hasn't been done. Certainly, we are interested in that. And I say no, but I should say that maybe it's already been done well enough to prove the point. I know that Nirala Singh, who's was the postdoc I talked about and is now an assistant professor at University of Michigan in chemical engineering there, he is trying to do just that kind of thing. So you might want to send him an email at University of Michigan. You know, so.
Great. The next question is from Sharat Maheshwari. It can be seen that the adsorption of these solvent molecules can affect the available active sites. Do you think they can also be used to or tuned to act as co-catalysts for elementary steps like coupled proton-electron transfer?
So can you read the first part of that sentence again?
So the first part is that, the solvent molecules can affect the available active sites.
Yeah, I understand. Certainly that's the case. You know, first thing that jumps to mind are I had a student who I was on the committee for who got her PhD in our chemical engineering department, and now she's a associate professor at Oregon State University. Her name is Line Ornedottir. She was a student of Hannes Jonsson, who did the nudged elastic band stuff. But she did work where she looked at the shuttling of protons and so forth due to the water solvent molecules in catalysis on platinum using DFT to look at those kinds of things. So certainly those effects are there, and I am not an expert about that. So
great. I guess the final questions from Ben Wang, Oklahoma. Nice talk. So in the metal oxide interface correlation, maybe one should include the lattice mismatch factor since it affects formation of metal oxygen bonds.
Yeah, I totally agree. And I would hope that we can work with theoreticians and get a better understanding of those adhesion energies and take those types of effects into consideration, because we are really having a hard time understanding these types of offsets between one metal and another, and why one metal differs. One oxide and another. Yes, good suggestion. We'd love to have input on that, those types of effects. What else goes into this? The mismatch might need to go into the maybe not this slope, but maybe the mismatch needs to go into the well, I'm having a hard time going backwards on my there. Maybe the offset in the y-axis offset, you know, maybe we're related to that or something. So not sure. A lot of work to be done to predict how different oxides affect adhesion energy. So.
Okay.
And I think what the slope of this is too. So.
Okay, great. So with that, I think we can end the public version, and
Okay.
I can continue with Charlie as well as some very interested students and postdocs. So I guess maybe what we can do, Charlie, is take like a 5-minute break or something and then return.
Oh, that would be good. Yeah.
Yeah.
That would be great. I'm
Yeah.
gonna get a cup